Welcome! In this session, we'll tackle an interesting problem: longest valid parentheses. This problem challenges us to find the length of the longest valid substring of parentheses in a given string, which is a great test of our understanding of stacks, dynamic programming, and string manipulation. Let's dive in and explore the different approaches to solve it. In this problem, we are tasked with finding the length of the longest valid parentheses substring in a given string S. The string consists only of the characters, and a valid parentheses substring is one where every opening parenthesis has a corresponding closing parenthesis, and the pairs are properly nested. For instance, is valid because it's balanced and well-formed, while is not valid since the order is incorrect. You need to return an integer representing the length of the longest substring that meets these criteria. Let's look at some examples to better understand the problem. In the first example, the input string is s equals. Here, the longest valid substring is, which has a length of 2. So, the output is 2. In the second example, the input string is s equals. The longest valid substring is, and it has a length of 4. Thus, the output is 4. These examples demonstrate how we find the longest sequence of balanced parentheses within the given string. Now consider the third example, where the input string is s equals. Since the string is empty, there are no valid parentheses substrings, so the output is 0. This highlights an important edge case where the input string contains no characters. Additionally, the constraints of the problem specify that the length of the string s can range from 0 to 10^4, and every character in s is either, or. Let's break down some other edge cases. If the string is empty, as we just saw, the output is 0. Similarly, if there are no valid substrings, such as an s equals, or s equals, the output will also be 0. On the other hand, if the entire string is valid and balanced, like s equals, the output should be the length of the string, which in this case is 4. Finally, if the string has unbalanced parts at the start or end, such as s equals, the function should still correctly identify and return the length of the longest valid substring within. These scenarios ensure that our solution handles all possible variations of the problem. To solve the problem of finding the longest valid parentheses substring, we began by considering the brute force approach. This is the most straightforward method, where we generate all possible substrings of the input string and check if each one is a valid parentheses sequence. A sequence is valid if every opening parenthesis has a corresponding closing parenthesis in the correct order. To implement this, we use two nested loops to generate all substrings, a helper function to verify their validity, and a variable to track the maximum length. However, while this approach is conceptually simple, it has significant drawbacks. Generating all substrings takes quadratic time, and checking each one for validity adds another layer of complexity, resulting in a time complexity of n cubed. This makes the method impractical for larger inputs, where efficiency is critical. Additionally, it requires extra space for the helper function stack, which further limits its utility. Next, we explored the dynamic programming approach, which leverages the idea that the length of the longest valid substring at a given index depends on previous indices. The core idea is to use a DP array where each element at index I represents the length of the longest valid substring ending at that position. The key observations here are that if the character at I is an opening parenthesis, it cannot form a valid substring on its own, so the value in the DP array remains 0. On the other hand, if it is a closing parenthesis that matches with an earlier opening parenthesis, we calculate the valid substring's length by referencing earlier indices. To implement this, we traverse the string and, for each closing parenthesis, check if it forms a valid pair by looking at the character at an index derived from the DP array. While this approach is much more efficient than brute force, with a linear time complexity of n, it requires additional space for the DP array. This makes it less optimal compared to approaches that can achieve the same result without extra storage. The stack-based approach offers another efficient solution. Here, we use a stack to track indices of unmatched parentheses. The main idea is that the difference between indices stored in the stack can give the length of valid substrings. Whenever we encounter an opening parenthesis, we push its index onto the stack. For a closing parenthesis, we pop the stack if it's not empty, which helps us find a matching pair. If the stack becomes empty after a pop, we push the current index as a placeholder. This helps in calculating valid lengths consistently by ensuring that the top of the stack always represents the last unmatched position. The method processes each character exactly once, giving it a time complexity of O(n). While it does require O(n) space for the stack, it is relatively simple to implement and is often preferred for its clarity. However, the need for additional space remains a slight drawback compared to other methods. Additionally, there's the two-pointer approach, which optimizes for space without the need for a stack. The two-pointer approach is a space-efficient alternative that uses counters to track the number of open and closed parentheses. It involves two passes through the string, one from left to right and the other from right to left. In the left to right pass, we increment counters for open and closed parentheses. Whenever the counts are equal, we calculate the length of the valid substring. If the count of closing parentheses exceeds the count of opening ones, we reset the counters. This ensures that we handle cases where the string becomes invalid midway. The right to left pass mirrors this process but handles cases where there are unbalanced closing parentheses at the start of the string. Together, these two traversals ensure that all edge cases are covered. This approach runs in linear time, O(n), and uses constant space, O(1), making it optimal in terms of memory usage. However, it requires careful handling of the counters, which can make the implementation slightly more error-prone compared to the stack-based method. After evaluating all approaches, we chose the stack-based method for its balance of simplicity, efficiency, and relatively low space complexity. While the two-pointer approach is optimal in terms of space, the stack-based method is easier to implement and debug. It also handles edge cases like an empty stack in a more intuitive way. The brute force method was ruled out early due to its impractical O(n)³ time complexity, which makes it unsuitable for real-world inputs. As for dynamic programming, while it achieves linear time complexity, it uses extra space for the DP array, which can be avoided with other approaches. Ultimately, the stack-based method strikes the right balance between computational efficiency and ease of implementation, making it the most practical choice for solving this problem while maintaining clarity and reliability in the solution. To solve the problem of finding the length of the longest valid parentheses substring, we begin by understanding what constitutes a valid substring. For parentheses, this means every opening parenthesis must have a corresponding closing parenthesis in the correct order. To tackle this efficiently, we use a dynamic programming approach. The idea behind dynamic programming is to solve smaller subproblems and use their results to build the solution for the overall problem. Here, we define a DP array where each element, DP I, represents the length of the longest valid substring ending at index I. We initialize all values in the array to 0, as a valid substring may not exist at certain indices. This structured approach enables us to systematically build up the solution as we process the string. Now, we traverse the string S starting from index 1, as a valid substring cannot end at the very first character. During this traversal, if the current character is an opening parenthesis, we skip it since a valid substring cannot end with. On the other hand, if the current character is a closing parenthesis, we analyze two cases. In the first case, if the previous character is an opening parenthesis, we form a valid pair, and update DP I by adding 2 to DP I2, provided I2 is a valid index. If it's not, we simply set DP I to 2, representing the pair itself. In the second case, if the previous character is also a closing parenthesis, we check if the character before the valid substring ending at I1 is a matching. If so, we update DP I by adding the length of the valid substring before this, along with the pair contribution of 2. This allows us to capture both nested and adjacent valid substrings efficiently. As we iterate through the string, we also maintain a variable, max_length, to track the maximum value in the DP array. This ensures that by the end of the traversal, we have the length of the longest valid parentheses substring. The use of dynamic programming is particularly effective here because the problem has an optimal substructure, meaning the solution at each index depends on solutions at earlier indices. This avoids redundant calculations and allows us to build the solution iteratively. Two key observations underpin this approach: valid substrings must always end with a closing parenthesis, and their lengths are determined by the positions of their matching opening parentheses. The DP array provides a way to efficiently compute these lengths without repeatedly recalculating results for previous indices. To implement this approach, we rely on two key data structures, the DP array and an integer variable max_length. The DP array stores the length of the longest valid substring ending at each index, requiring n, space where n is the length of the string. The variable max_length tracks the maximum length found during the traversal, and it has a constant space requirement. In terms of complexity, the time complexity of this solution is n, since we process each character in the string exactly once. The space complexity is also n, due to the DP array. This combination of linear time and space ensures the algorithm is both efficient and scalable. By structuring the problem this way, we achieve a balance between clarity and computational efficiency. Let's walk through an example to see the algorithm in action. Consider the input string s equals. We initialize the DP array as 0, 0, 0, 0, 0, 0, and set max_length equals 0. At index 1, the character is, and the previous character is, forming a valid pair. We update DP 1 to 2 and set max_length to 2. At index 2, the character is, so we skip it. At index 3, the character is, and the previous character is, forming another valid pair. We update DP 3 to 4 by adding 2 to DP 1, and max_length becomes 4. At index 4, the character is, so we skip it. At index 5, the character is, and the previous character is, forming yet another valid pair. We update DP 5 to 6 by adding 2 to DP 3, and max_length becomes 6. This step-by-step process demonstrates how we iteratively build the solution. After processing all characters, the final DP array is 0, 2, 0, 4, 0, 6, and the maximum length of a valid parentheses substring is 6. This result is returned as the final answer. When considering edge cases, the algorithm handles various scenarios effectively. For an empty string, the result is 0 since there are no characters to form a valid substring. For a string with only opening parentheses, such as, the result is also 0 because there are no closing parentheses to form pairs. For disjoint valid substrings, like in, the algorithm correctly calculates the total length as 4. Finally, for strings with a mix of nested and disjoint substrings, such as, the algorithm accurately identifies and combines the contributions of each valid substring. This robustness makes the solution both comprehensive and reliable. The provided Python code solves the longest valid parentheses problem using a dynamic programming approach. Let's go through the code step by step. 1. Initialization. The function starts by calculating the length of the input string s. If the string length is less than or equal to 1, it returns 0 because a valid parentheses substring cannot exist in such cases. 2. Dynamic programming array. A DP array of size n, same as the length of s, is initialized with all zeros. This array will store the length of the longest valid parentheses substring ending at each index. 3. Iterating through the string. The loop starts from index 1, since a valid substring cannot end at index 0. The goal is to populate the DP array based on the current character and its relationship with the previous characters. For case 1 simple pair, if the current character is, and the previous character is, it forms a simple valid pair. The length at DP I is updated to 2 plus the value at DP I2, if I equals 2, to account for any preceding valid substring. 5. Case 2 nested or consecutive valid substrings. If the current character is, and the substring before the current valid substring, tracked by DP I1, is, it indicates a nested or consecutive valid substring. The length at DP I is updated by adding the length of the previous valid substring, DP I1, the length of the valid substring before the matched opening parenthesis, if any, and 2 for the current matching pair. 6. Updating the maximum length. After updating DP I for each valid case, the global max_length variable is updated to keep track of the longest valid substring encountered so far. 7. Returning the result. At the end of the loop, the function returns the max_length, which represents the length of the longest valid parentheses substring in the input string. This solution has a time complexity of n, as it processes each character of the string once, and a space complexity of n, due to the DP array. It efficiently handles edge cases and ensures correctness by carefully checking the conditions for valid substrings. Here, we start by defining a method called longest valid parentheses, which takes a string s as input. First, we determine the length of the string and handle the base case where the length is 1 or less, immediately returning 0 since no valid parentheses can exist in such cases. Next, we declare a dynamic programming array, dp, to store the maximum length of valid parentheses ending at each index. We also initialize a variable maxLength to keep track of the global maximum length found so far. Now, we loop through the string starting from index 1, as valid parentheses must involve at least 2 characters. Inside the loop, we check if the current character is a closing parenthesis. If it is, we proceed to evaluate 2 cases. In the first case, if the previous character is an opening parenthesis, we have a simple pair, and we update the dp value at the current index. If the index is greater than or equal to 2, we add the dp value from 2 indices back to account for any valid sequences preceding the pair. Otherwise, we simply add 2 for the current pair. In the second case, we handle nested or consecutive valid strings. Here, we check if the index before the current valid substring is within bounds and if the character at that position is an opening parenthesis. If it is, we compute the dp value by adding the length of the previous valid substring, the dp value from 2 indices before the current valid substring, if it exists, and 2 for the current valid sequence. After updating the dp value for either of these cases, we compare it with the global maxLength and update maxLength if the current dp value is greater. Finally, once the loop completes, we return the maxLength variable, which contains the length of the longest valid parentheses substring in the input string. We begin with the input string s equals. First, we initialize some variables. N is the length of the string, which is 3. We create a dynamic programming array dp with 3 elements, all set to 0, to track the length of the longest valid parentheses ending at each index. We also initialize max_length as 0 to keep track of the global maximum length. Now, during the first iteration at index I equals 1, the character is. Since an opening parenthesis cannot form a valid substring on its own, we skip further processing at this index. The state of our variables remains as dp equals 0, 0, 0, and max_length equals 0. Next, at index I equals 2, the character is. Here, we check if the previous character s, I1, is. Since it is, this forms a basic valid pair. Using the formula dp, I equals dp, I2 plus 2, we calculate dp, 2, as 0 plus 2, which gives us 2. We then update max_length to the maximum of its current value in dp, I, resulting in max_length equals 2. The updated state is dp equals 0, 0, 2, and max_length equals 2. After completing the iterations, the final output for this example is the longest valid parentheses substring, which is of length 2. Now, let's look at the next example with the input string s equals. First, we initialize the variables. The length n of the string is 5. We create a dp array with 5 elements, all initialized to 0, and set max_length to 0. During the first iteration at index I equals 1, the character is. Here, we check if the previous character s, I1, is. Since it is, this forms a basic valid pair. We update dp, I, using the formula dp, I, equals dp, I2, plus 2. With dp-1, considered as 0, we calculate dp-1, as 0 plus 2, resulting in 2. We then update max_length to max, 0, 2, which is 2. The updated state is dp equals 0, 2, 0, 0, 0, and max_length equals 2. In the second iteration, at index I equals 2, the character is. Since an opening parenthesis cannot close any valid substring, we skip further processing at this index. The state remains unchanged with dp equals 0, 2, 0, 0, 0, and max_length equals 2. Similarly, in the third iteration, at index I equals 3, the character is also. Again, we skip processing, and the state remains the same. Now, at index I equals 4, the character is. We first check if the previous character s, I1, is. Since it is, this forms a basic pair. Using the formula dp, I, equals dp, I2, plus 2, we calculate dp, 4, as dp, 2, plus 2, which gives 2. We then update max_length to the maximum of its current value n dp, I, which remains 2. The updated state is dp equals 0, 2, 0, 0, 2, and max_length equals 2. Finally, the longest valid parentheses substring for this example is of length 2. Now, we turn to the input string s equals. We initialize the variables. N is 6, the dp array has 6 zeros, and max_length starts at 0. In the first iteration, at index I equals 1, the character is. Checking the previous character s, I1, which is, we find a basic valid pair. Using the formula dp, I equals dp, I2 plus 2, we calculate dp, 1, as 0 plus 2, resulting in 2. We then update max_length to max, 0, 2, which is 2. The updated state is dp equals 0, 2, 0, 0, 0, 0, and max_length equals 2. In the second iteration, at index I equals 2, the character is. Since an opening parenthesis cannot close a valid substring, we skip processing this index. The state remains as dp equals 0, 2, 0, 0, 0, 0, and max_length equals 2. Similarly, in the third iteration, at index I equals 3, the character is also. Again, we skip processing, and the state remains unchanged. At index I equals 4, the character is. First, we check if the previous character s, I1, is. Since it is, we form a basic pair. Using the formula dp, I equals dp, I2 plus 2, we calculate dp, 4, as dp, 2 plus 2, which gives 2. Additionally, we check for a nested valid substring. Since s, idp, I1, -1 is, we update dp, I to dp, I1 plus dp, idp, I1, -2 plus 2. Calculating this, dp, 4, becomes dp, 3 plus dp, 0 plus 2, which equals 4. We then update max_length to max, 2, 4, resulting in 4. The updated state is dp equals 0, 2, 0, 0, 4, 0, and max_length equals 4. Finally, at index I equals 5, the character is. We skip the basic pair check since s, I1, is not. Instead, we check for a nested valid substring. Here, s, idp, I1, -1 is, so we update dp, I to dp, I1 plus dp, idp, I1, -2 plus 2. Substituting values, dp, 5, becomes dp, 4 plus dp, -1 plus 2, which calculates as 4 plus 0 plus 2, giving 6. We then update max_length to max, 4, 6, resulting in 6. The final state is dp equals 0, 2, 0, 0, 4, 6, and max_length equals 6. The longest valid parentheses substring for this example is of length 6. The time complexity of this dynamic programming solution is O, n, where n is the length of the input string. To understand why, let's break it down step by step. First, we initialize a dp array of size n, which takes O, n, time. Then, the main loop iterates through the string from index 1 to n1, resulting in n1 iterations, which is still O, n. Inside this loop, we perform constant time operations like comparisons and arithmetic calculations, as well as updating the dp array. Even when we access previous values in the dp array, such as dp, I2, or dp, I1, 2, these lookups are O1. Finally, updating the maximum length using max_length, dp, I, also takes constant time. Since the loop processes each character of the string exactly once, and all operations inside are O1, the total time complexity sums up to O, n. Combining all these steps, the overall time complexity of the solution remains O, n. Now, let's examine the space complexity. The primary contributor is the dp array, which is used to store the maximum length of valid parentheses ending at each index. Since this array has a size of n, it requires O, n, space. In addition to the dp array, we use a few scalar variables, such as n, max_length, and the loop counters. These variables only take up constant space, or O1. Therefore, the total space complexity is dominated by the size of the dp array, which makes it O, n. To better understand the efficiency of this approach, let's compare it to the brute force method. A naive solution would involve checking all possible substrings of the input string to determine if they represent valid parentheses. For a string of length n, there are O, n squared, substrings, and validating each substring takes O, n, time. This leads to a time complexity of O, n cubed, for the brute force approach. In contrast, our dynamic programming solution reduces the time complexity to O, n, by storing intermediate results in the DP array and avoiding redundant computations. However, both approaches share the same space complexity of O, n, as the DP array is the dominant factor in the dynamic programming approach, while the brute force method generally uses no additional data structures and therefore has O, 1, space complexity. Now, let's analyze the performance in different scenarios. In the best case, the input string is either empty or contains no valid parentheses. Even then, the loop still iterates through the string, making the time complexity O, n. In the average case, the string contains a mix of valid and invalid parentheses. Here, the DP array allows the solution to efficiently compute results without redundant calculations, maintaining the time complexity at O, n. For the worst-case scenario, imagine the entire string consists of valid parentheses, such as a long sequence of open and close pairs. Even in this case, the solution processes each character only once, ensuring the time complexity remains O, n. Across all cases, the space complexity stays constant at O, n, due to the DP array. To validate the O, n, time complexity mathematically, consider the main loop. It iterates n1 times, and each iteration involves constant time operations, such as comparisons, arithmetic calculations, and updating the DP array. This gives us O, n1, O1, which simplifies to O, n. On the space complexity side, the DP array, which stores intermediate results for each index, dominates the memory usage. Since the array has a size of n, the space complexity is O, n. In summary, the dynamic programming solution offers significant efficiency improvements over the brute force approach, achieving O, n, time and O, n, space complexities. This makes it well-suited for processing even large input strings efficiently. Let's continue. Let's continue. Let's continue. Let's continue. Thank you for joining. Today, we explored the longest valid parentheses problem and learned how different approaches like stacks and dynamic programming can help us solve it effectively. Remember, practice is key to mastering these techniques. Be sure to like, share, and subscribe for more insights and solutions. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!